Assalamualaikum warahmatullahi wabarakatuh and hi. We're going to be discussing about the behavior of materials under deformation. These are some of the terms that we need to be familiar with because you're going to see these terms quite a lot in this chapter. So we have number one, strength, which is the ability of a material to withstand a force without breaking. And we call the material stiff if it resists any changes in shape and size. And elasticity, which we're going to see a lot, and we're going to be discussing this in a second. It's the tendency of solid objects and material to spring back to their original shape after the external forces that are causing the deformation are removed. For ductility, it's the tendency of a material to change its size and shape significantly before breaking. And lastly, we have brittleness, that is a tendency of a material to break without any deformation. We have a table right here showing some of the examples of elastic and inelastic materials. Sponge, spring and rubber are some of the examples of elastic material, and we have paper, metal and plastine for inelastic material. As we saw just now, elastic material are the material that is able to return to its original shape after being deformed, and the opposite is true for inelastic material. Okay, we have a figure right here showing a spring. So we have a spring right here with the length of L0. So this is the original length of the spring. After that, we put a weight at the end of the spring, and as a result the spring is elongated. So we have some extension right here. It's labeled as delta x. How do we determine delta x? Delta x is equal to L1 minus L0. The load that we have right here has a weight which is equal to mg, and we are increasing the slotted mass, and consequently the weight are also increased. So you can see that as we add the weight to the end of the spring is extended to a certain extent, and then we reduce the slotted mass until it's completely zero, and then we take out the weight at the end of the spring. So you can see that at the end of at the last stage of this figure, the spring it's able to return to its original length, which is L0. So this is what we meant by elastic material. So after we are removing the external force to the end of the spring, it returns to its original length. Alright, this is stress versus strain graph for force versus extension. Stress versus strain graph is on the right here. On the left, we have force versus extension graph. We have quite a few points right here: A, B, C, D, and E. Elastic deformation, plastic deformation. Let's talk about this now. So for points A, B, C, D, and E are labeled right here as proportionality limit. B is elastic limit. Yield point is labeled as point C. And then at the peak right here, we have point D, which is maximum force point. And the last one is fracture point. So what does all this point mean? Let's look at point O to point A. Point O is the origin of the graph. It's right here. From point O to point A, the graph is a straight line where stress is directly proportional to the strain. We can also see the extension is directly proportional to the force because along the region OA, wire obeys Hooke's law. We learned about Hooke's law in the earlier chapters, where F is equal to Ke. E is the extension of the wire, K is spring constant, and F is the amount of force. When the stress is removed, the wire returns to original length because this is under elastic deformation. The wire still experiences the elastic deformation, and the straight line portion, it ends at point A. That's why we call it proportional limit, because this is where the proportionality ends. For point A to point B, this line AB, along this line, stress and strain are no longer proportional, and also Hooke's law is not obeyed, but wire still shows some elastic behavior because it's still in elastic deformation region. B is the point known as elastic limit. Along this path, OAB, when the stress that we apply to the wire is removed, the wire will spring to its original length. But beyond point B, when you apply stress beyond point B, the wire will be permanently stretched and it will never regain its original shape or length. Okay, this is some explanation about elastic deformation. It is also called a temporary deformation because this process is reversible when you apply a certain force to the material or the wire, like we saw in the figure with spring and load. It returns to its initial condition. So it's also known as a temporary deformation in which the object can regain its original shape when external force is removed. Okay, CDE, along points CDE, along that line, we have plastic deformation, and plastic means permanent deformation. Okay, permanent deformation is when the object cannot regain its original shape when external force is removed. You can think of this as having a plastic surgery. If you're planning to have a plastic surgery, you have to know that once you do the plastic surgery to your face or any parts of your body, it's permanent. So we can no longer return to our natural face. Okay? So plastic deformation is a permanent change in an object's shape and size, and this is an irreversible process. Okay, point C. What is point C? The point C is called a yield point. This is where plastic deformation starts. So if you were to remove stress at this point, it won't get back to point O as we started with. It would be slightly longer, because the wire now has a permanent extension OP when the force is removed. When the stress is further increased, strain will increase also, and in a very rapid manner. CD is when the wire experiences plastic deformation. It's still in plastic deformation region, and we said that once the material becomes plastic, even though a tiny amount of stress is applied, we're going to observe a relatively large increase in strain. Point D, which is at the peak right here, or the crest, this is called maximum force point. So this is when maximum amount of stress is applied to that object, and at this point the wire thins and necks are formed, as shown in this figure. Okay then, what is line DE? Line DE is when the diameter of wire becomes extremely small and uneven. And finally at point A, the wire will eventually break. So this is the point where we call fracture point. Okay, I think that's all. Thank you. Thanks for watching and have a nice day.